So good morning, and this is all about diffraction gratings and caused by double slit interference. So instead of the sources of waves that you had with the double source interference, we're going to do that by replacing it by diffraction from two slits. So you can see this is just a this is just a reminder of diffraction from National 5, that if you've got waves approaching an obstacle, the waves can creep around the side and diffract there, and it works better with long wavelengths, but if you do it with a very small slit there, you get really good diffraction, which appears to be just the same as a single source. So this shows you here that you've got water waves coming out to double slits, and then you start to get this interference pattern coming through here. Often drawn this way now, so this is the same sort of pattern that you were seeing yesterday, where we've got lines of constructive and destructive interference. Again, circular wavefronts, but the two circular wavefronts, semicircular wavefronts, come from the two slits here, so you've got diffraction happening. What you see on a screen, if you're doing this with light, is you see a central maximum. So that's your first bright fringe. You have dark fringes, bright fringes, dark fringes, where you've got destructive, constructive, destructive. Bear in mind that at these points here, the waves are arriving in phase, out of phase, in phase, out of phases for the destructive and constructive interference. You're going to watch this video fully in a moment to work out the method for working out the wavelength of laser light. So I'm just going to pause it here. You can see what you're seeing on the screen here is the bright and dark fringes, and the experiment measures those for you and allows you to get some measurements. You'll also be asked to try and find out a little bit more about how this is the definitive proof that light was a wave, and Sir Thomas Young came up with this experiment, hence it's called Young's double slit experiment. And funnily enough, Isaac Newton was on the other side of the fence saying that light was actually particles or corpuscles. So Newton was kind of wrong at the time, but then of course the photoelectric effect came along and settled the argument by proving them both right. But key experiment here in terms of the wave nature of light. Light is often a mismatch of different wavelengths, frequencies and phase. So the light that we get from the sun has got lots of different colours, different wavelengths, and they all arrive at different times. You can have what's called monochromatic light. So monochromatic light from an LED or a sodium discharge light will have all the same frequencies, but they will all be doing their own thing at different times. A laser and other coherent light sources, so a light source is coherent only if the waves have a constant phase relationship. So the light goes up, down, all at the same time. So all these individual photons are completely in step and synchronized. So that gives us a coherent wave source. And interference works best with a coherent wave source. There's a Minute Physics video here that shows it quite nicely, so you can have a look at that as well when you're playing back the slides there. I'm going to move on to the equation which defines this, and the equation that explains things like as you move the slit spacing together, so here's S1 and S2 being pulled together, what you can see, if it'll play itself again there, is that the fringe spacings, the areas of maximum and minimum, pull apart, so have a bigger angle of interference the closer the slits are together. If we do the same thing with the wavelength, if we increase the wavelength, so you can see the wavelength is getting longer and longer, again, that fringe spacing gets further and further apart. You'll see it yourself when you play it back. So to do that, we analyze the rays coming from the light source. So here's our laser. There's the two slits in the gap there. And that causes a central bright fringe over here, central maximum, and also causes your first bright fringe. This is the first of those tiny wee red dots that you saw there. The reason you've got that maximum there is because the waves arrive in phase. So there's two red photons arriving in phase, giving you constructive interference. That's because the bottom ray has travelled one extra path difference of one full wavelength. Okay, so constant interference, one path difference there, and that's the distance there. We're going to try and show this equation. So if we go to the second maximum and Oops, here we go. Yeah, sorry, I forgot to do the actual rearranging here. So if we look at this right angle triangle in here, so we've zoomed in on it and we've said that's a right angle triangle because that's the extra path difference, and from there on both lines are the same distance, so that means that that must be a right angle in there, and if that's a right angle, that angle in there is 90 minus theta, and if that's 90 minus theta, then that must be theta over there. It could be, for example, that was 10 degrees, in which case that would be 80, and therefore that must be 10 in the triangle. So we've got a right angle triangle with the hypotenuse d, the opposite side lambda, and we're trying to find what theta is. So you're just using sine theta, lambda over d, and you rearrange that to give you d sine theta equals lambda. So we're getting close to the equation that we're after. If we look at this now for the second maximum, so there's our first maximum, there's the second maximum, there's now a path difference of 2 wavelengths. So same kind of right angle triangle, it's had to travel 2 lambda more to give us the second area, the second order maximum. And so same thing, sine theta opposite over the hypotenuse, 2 lambda over d, rearrange that and you get d sine theta equals 2 lambda now for our second order maximum. In fact, you can do that for any number maximum, however many number of wavelengths that you have as path difference for the mth order over here, then you rearrange that and you get this equation d sine theta equals m lambda, and that is the Young-Slits or diffraction grating equation which you get on the formula sheets. That's the slide that I'll ask you to copy in your notes later, which has got all the information just on one slide, which you can pop into your notes there. This works with extra slits, so if you keep adding, if that's just with 2 slits there, you'll end up with the extra waves coming out there, and they actually all constructively interfere at each of those dots where there would have been a bright fringe. You end up with a series of dots from a diffraction grating, and I'll show you this next week. You will see this. But all you do is it's brighter and it's just more detailed. So a diffraction grating with lots of slits actually works better than just double slits. And a diffraction grating is it's simply a bit of glass where there are lines etched on it, and the lines stop the light from getting through where there's been a line etched, but only where you've got the clear glass left on top, that's where the light gets through. And the spacing, the slit spacing, is determined by the number of lines that there are per meter. So you can see here this one's got 600 lines per millimeter. That would be 600,000 lines per meter, and you'd need to work out the slit spacing as being 1 divided by 600,000. Always get these both dimensions with the diffraction grating equation in meters. Don't try and they've got to be in the same units, that's for sure, and meters is the best one to use. So I'm going to ask you to have a go at this example using the equation there. You'll then check your answer over on the next slide. Then I'm going to ask you to go over the questions of activity 5 and check your answers on those. Then a chance to look that video again up with the laser wavelength experiment. I've given you how you'll get the wavelength using trigonometry on the data that's given in the video. Then going to have a go at a simulation, and you're going to vary all the different things that I've suggested on those settings, suggested settings there, using the slits simulation setting there. So play around with that and try different frequencies and things like that there. But it works best with the light source because then you can see the screen and see where the bright and dark fringes are over there. And you are picking on 2 slits to make it work best. And then there's some other notes to put in, because what you'll find out is what happens when you change the grating lines closer together or the wavelength of the light is increased. More or less what I said before, but you can see it for yourself. And then finally there's an example question to try more of an describe and explain effect question based on what you've done. So that's what you should have done by the end of it all there. After that there'll be a Google form quiz and then a little bit of research about Thomas Young and the corpuscular theory of light, which he managed to overturn. So a lot to do in a double period, and as I say, if you're stuck with what it means or anything, put in a comment and I'll get back to you as soon as. Good luck.